Most parents searching for AI projects for their kids are asking the wrong question. They want something their child can knock out over the weekend, maybe impress the science fair judges. But here's what they should actually be asking. What sequence of skills does my child need to contribute to a $15.7 trillion economy? I'm Rajiv Patel, and I've mapped out the real progression from block-based pattern recognition at 7 years old all the way to deploying supervised learning models at 15. This isn't about entertainment, it's about building a legitimate skill stack.
You're listening to the STEM Lab podcast. Quick thing I want to mention up front. Everything you're hearing, the research, the data, the script itself, that's all human verified and written by real people. But the voice you're hearing right now, that's AI generated. Just want to be transparent about that. If you've been listening for a while, thank you, honestly. You're the reason this show exists. And if you're brand new here, welcome aboard. We put out new episodes every Monday, Wednesday, and Friday, so you've got a pretty steady stream of content coming. Let's get into today's episode. This checklist maps concrete AI projects against actual skill progression. Each project builds toward industry-standard competencies: Python fluency, dataset management, model training, algorithmic thinking. No fluff projects here. No AI art generators that teach absolutely nothing about the underlying mechanics. Just a clear roadmap from foundational logic to deployable machine learning systems. I'm assuming you're evaluating long-term skill acquisition, not just entertainment value. The projects are organized by technical capability rather than arbitrary age brackets, because honestly, a motivated 10-year-old with prior Scratch experience will outpace an unmotivated 13-year-old starting cold every single time. I've structured this around the same learning path I use with my own children and recommend to hiring managers looking for junior ML engineers. Now, let's start at the beginning. Pattern recognition and decision trees for ages 7 to 10. No prior coding required. These projects introduce core concepts like classification, training data, and rule-based logic without requiring text-based programming. Expect 8 to 12 weeks to complete this tier before advancing. First up, image sorting with supervised card games. This is physical card decks where children manually sort images of animals, vehicles, food items, and create written rules for classification. It builds understanding of labeled training data and feature identification. You don't need any equipment beyond printed image sets. This prepares them for supervised learning concepts that appear in actual ML workflows. Next, teachable machine projects via Scratch integration. Google's Teachable Machine exports models directly to Scratch 3.0. Children train image classifiers, think hand gestures or facial expressions, and integrate them into Scratch games. You'll need a webcam, Chrome browser, and the offline Scratch 3.0 desktop app if you want air-gapped use. This demonstrates the train, test, deploy cycle without Python syntax getting in the way. Then there's decision tree board games. Physical flowchart construction using 20 questions mechanics. The child creates branching yes-no decision trees to identify objects, then tests those trees against family members. This teaches tree depth, overfitting when trees get too specific to training examples, and generalization. Zero cost beyond paper and markers. It directly maps to Scikit-learn's decision tree classifier logic used in production systems. Lego sorting algorithms work really well here too. Manual sorting of Lego bricks by color, size, then both attributes simultaneously. Children document their sorting rules and measure accuracy when a sibling introduces test set pieces. This introduces multivariable classification and confusion matrices. How many red 2x4 bricks were misclassified as red 2x2s? It links naturally to robotics kits that automate similar sorting tasks later in the learning path. Voice command training with Scratch uses Scratch's speech recognition blocks. Children build voice-controlled sprite animations. They document which commands work reliably versus which fail, introducing the concept of model accuracy and natural language ambiguity. requires a microphone, works offline with Scratch 3.0 desktop, sets the foundation for later natural language processing projects. And finally, for this tier, rule-based chatbot flowcharts, paper-based conversation flowcharts where children map user inputs to bot responses. They test their chatbot logic by having parents follow the flowchart verbatim, which exposes gaps in their decision trees. No coding required, prepares them for Python-based chatbot implementation at intermediate level. Moving on to intermediate level, supervised learning with Python for ages 10 to 13. This requires Python fundamentals. Projects in this tier require proficiency with Python variables, loops, and functions. Children should complete a screen-free coding to text-based transition before attempting these. Expect 15 to 20 hours per project. First, image classifier with teachable machine plus Python. Export teachable machine models to TensorFlow format, load them in Python using TensorFlow.js or Keras, and run inference on new images. Children learn model import workflows, understand file formats like .h5 and .json, and handle prediction outputs. Requires Python 3.8 or later, TensorFlow 2.x, 8 gigs of RAM minimum. This introduces dependency management, pip install, and virtual environments, which are skills used in every professional ML workflow. Spam filter using naive Bayes is next. Collect 100+ emails, half spam, half legitimate. Extract text features like word frequency, train a scikit-learn naive Bayes classifier, and test accuracy. Children learn data collection ethics, text pre-processing, removing punctuation, lowercasing, and the importance of balanced datasets. Requires Python 3.x, scikit-learn, and pandas. Outputs confusion matrix and accuracy metrics, the same evaluation tools used in enterprise sentiment analysis systems.
Handwritten digit recognition with MNIST. Load the classic MNIST dataset, visualize digit images using matplotlib, train a simple neural network with Keras, and evaluate accuracy. Children encounter real neural network architecture decisions, number of layers, activation functions, and they see how training epochs affect performance. Requires Python 3.8 or later, TensorFlow 2.x or PyTorch, 16 gigs of RAM recommended for reasonable training speeds. This project directly parallels image recognition tasks in autonomous vehicle development. Weather prediction from CSV data is another solid project. Download historical weather data, temperature, humidity, precipitation, clean the dataset in pandas, train a regression model to predict tomorrow's temperature and calculate prediction error. Introduces time series data, feature engineering like day of year or month, and train test split mechanics. Requires Python 3.x, pandas, scikit-learn. Data is available from NOAA or similar government weather services. Teaches the same regression techniques used in demand forecasting and financial modeling. Rock, paper, scissors AI with pattern detection rounds out this tier. Build a Python program that plays rock, paper, scissors by detecting patterns in human choices, frequency analysis, streak detection. Children implement their own algorithms rather than using libraries, which forces them to think through probability and prediction logic. Requires only base Python installation. Demonstrates how simple statistical analysis can outperform random guessing, a core insight in many ML applications. Now let's talk about advanced level. Deep learning and model training for ages 13 and up. This requires calculus concepts and GPU access. These projects demand understanding of derivatives, loss functions, and gradient descent. Children need access to GPU hardware, NVIDIA GTX 1060 or better, or cloud GPU credits. Projects take 30 to 50 hours each. Custom image classifier with transfer learning. Download a pre-trained ResNet or MobileNet model, freeze base layers, add custom classification layers, train on a self-collected image dataset, 500+ images minimum, and deploy via Flask web app.
Children learn transfer learning economics. Why retrain everything? They also learn data augmentation techniques and API deployment. Requires Python 3.8 or later, TensorFlow 2.x or PyTorch, CUDA-compatible GPU, 32 gigs or more storage for datasets. This workflow mirrors exactly what ML engineers do in production environments, repurposing existing models for new classification tasks. Understanding of neural networks is prerequisite.
Natural language chatbot with transformer models. Fine-tune a lightweight transformer model, Distill-BERT or GPT-2 small, on domain-specific conversation data. Implement context tracking across multi-turn conversations and measure response relevance. Children encounter tokenization, attention mechanisms, and the computational cost of large language models. Requires Python 3.8 or later, Hugging Face Transformers library, 12 gigs or more GPU VRAM for training, introduces model quantization and optimization techniques used to deploy models on resource-constrained devices. Reinforcement Learning Game Agent. Implement Q-learning or deep Q networks to train an agent that plays a simple game like cart pole or a Pong clone. Children manually code the reward function, implement epsilon greedy exploration, and visualize how policy improves over training episodes. Requires Python 3.8 or later, OpenAI Gym, Stable Baselines 3, or custom implementation. GPU recommended, but not required for simple games. This is the same algorithmic approach used in robotics path planning and industrial control systems. Object detection with YOLO, that's You Only Look Once model, on a custom dataset of household objects. Implement bounding box annotation and deploy real-time detection via webcam. Children learn annotation workflows, tools like label image or similar. They understand intersection over union metrics and confront the speed-accuracy trade-off in real-time systems. Requires Python 3.8 or later, Darknet or Ultralytics YOLO v5, CUDA-compatible GPU with 8 gigs or more VRAM, webcam. Directly applicable to autonomous robotics and surveillance systems. Pairs well with Arduino robotics platforms for physical object detection applications. And finally, Generative Adversarial Network, or GAN, for synthetic images. Implement a basic GAN architecture that generates synthetic images, faces, digits, or textures. Balance discriminator and generator training and visualize mode collapse. Children encounter adversarial training dynamics, latent space manipulation, and the instability inherent in GAN training. Requires Python 3.8 or later, TensorFlow 2.x or PyTorch, 16 gigs or more GPU VRAM, significant compute time, 12 to 24 hours training. This architecture powers synthetic data generation in industries with limited real-world data availability, medical imaging, rare failure modes in manufacturing. Here's a condensed checklist to verify project readiness before starting. Hardware verification. Confirm compute requirements, RAM, GPU, storage, match your available hardware. Cloud alternatives like Google Colab or AWS SageMaker provide temporary GPU access but introduce dependency on internet connectivity and subscription costs.
Software environment. Verify Python version, install required libraries, test imports before starting. Use virtual environments, VENV or Conda, to isolate project dependencies. Dataset availability. Confirm access to training data, understand licensing restrictions. Many datasets prohibit commercial use. Assess dataset quality, label accuracy, class balance. Time allocation. Block 2 to 3 hour work sessions minimum.
ML training requires uninterrupted focus. Context switching destroys momentum. Learning path position. Verify prerequisite skills are solid before advancing tiers. Skipping foundational work creates compounding knowledge gaps that surface as "I don't understand why this doesn't work" frustration later. Output validation. Define success criteria before starting. Target accuracy percentage, qualitative behavior goals. "It works" is insufficient. Specify measurable outcomes. Let me answer some questions that come up constantly. What prerequisite math skills do kids need before starting intermediate AI projects? Children need comfort with percentages, basic statistics like mean and mode, and simple algebra, variables and equations for intermediate projects. Advanced projects require understanding derivatives conceptually, rate of change, slope, and matrix operations, multiplication, dot products. Most ML libraries abstract the calculus implementation, but children who can't conceptually grasp adjusting weights based on error gradient will struggle with debugging and hyperparameter tuning. If your child hasn't covered derivatives in formal coursework, visual explainers showing gradient descent as walking downhill provide sufficient conceptual foundation to start. Full calculus fluency becomes necessary only when implementing custom loss functions or novel architectures. How do AI learning kits compare to building projects from scratch in Python? Packaged AI learning kits accelerate initial exposure by eliminating environment setup friction. You unbox hardware, run provided software, and see immediate results. They work well for demonstration and proof of concept understanding, but constrain customization. Building from scratch in Python develops transferable skills: debugging cryptic error messages, reading documentation, managing dependencies, and structuring projects, the unglamorous work that comprises 80% of professional ML engineering. I run my own children through both. Kits for initial concept exposure, then immediate transition to Python implementation of the same concepts. The kit provides motivation and context. The Python work builds employable skills. Can younger kids work on AI projects without understanding the underlying math?
Yes, at the beginner level detailed above, but with clear limitations. Pattern recognition, decision trees, and supervised learning via visual tools teach classification thinking and model training workflows without requiring mathematical formalization. This builds intuition that makes later math instruction more concrete. However, progression beyond basic supervised learning requires understanding probability, confusion matrices, accuracy metrics, algebra, feature weighting, linear relationships, and eventually calculus for gradient descent. Attempting advanced projects without mathematical foundation produces children who can follow tutorials but cannot debug failures, optimize models, or adapt techniques to novel problems. The goal is not entertainment, it's building toward career-viable competency, which requires mathematical literacy by age 13 or 14. Here's what you need to understand. The AI projects listed here represent a 3-year minimum progression from pattern recognition to deployable models. Rushing through tiers produces shallow familiarity rather than transferable skills. Current hiring data shows demand for mid-level ML engineers, 3 to 5 years experience, outpacing entry-level positions 3 to 1. Employers want people who can implement, debug, and optimize existing models, not just conceptually discuss AI. A 15-year-old who has completed the intermediate tier projects above demonstrates more employable capability than many undergraduate CS majors. The key differentiator? They've debugged real training failures, managed real datasets, and deployed working systems. Theory matters, but production competency gets hired. Start with decision trees this month. By 2029, your child could be training production models while their peers are still deciding which college major to choose.
That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. We've got new episodes dropping every Monday, Wednesday, and Friday, so you won't be waiting long for the next one. If you found this helpful, I'd really appreciate it if you leave a 5-star rating and write a quick review. That's genuinely how other people find the show, and it makes a bigger difference than you'd think. And hey, hit subscribe or follow so you get notified the second a new episode goes live. I'll see you in the next one.